Inside pretty much every car engine, there's this hidden battle going on, thousands of times a minute. It's a fight against a force that's trying to tear the engine's core apart from the inside out.
All right, so let's jump right in with a pretty simple question. When an engine's running, you'd think the main rotating part, the crankshaft, would just spin perfectly smoothly, right? I mean, that makes sense. But the reality is actually way more violent.
So the answer really comes down to how an engine makes its power. See, it's not this smooth, constant flow you'd get from, say, an electric motor. No, it's more like a series of perfectly timed and really powerful punches. Think about it. Every single time a cylinder fires, it's basically a tiny explosion that just slams down on a piston. And that delivers this massive, instantaneous spike of torque. That's the twisting force, right onto the crankshaft. We're not talking a gentle push here. This is a sudden, jarring hit. And what that does is create this frantic push-pull cycle. So first, you get a combustion event in one cylinder, and bam! It accelerates the crankshaft. But almost instantly, you've got the next cylinder in line compressing its air and fuel. And that, plus all the friction inside the engine, starts slowing the crankshaft right back down. So it's this constant speed up, slow down, thousands of times every minute. Okay, but here's where it gets really interesting. It's all about how the crankshaft itself responds to these punches. We tend to think of it as this perfectly rigid, solid piece of steel, but it's really not. This constant speeding up and slowing down actually causes the crankshaft to physically twist along its own length. The front end of the shaft will move just a little bit before the back end does, and then it springs back. This tiny microscopic twisting and untwisting, well, that's what engineers call torsional vibration. And here's a great way to picture it. Imagine you have a long rubber rod. If you grab one end and give it a quick twist, you can actually see the twist travel down its length, right? The other end doesn't move at the same time. Well, believe it or not, a solid steel crankshaft does the exact same thing. It's just happening on a scale that's totally invisible to us. So the really crucial thing to get here is that this vibration doesn't come from just one thing. Nope. It's like a perfect storm. You've got those violent power pulses, you've got the crankshaft's own natural springiness, and you've got the sheer weight, the inertia of all the pistons, connecting rods, and the flywheel that it has to lug around. All right, so this tiny little twist, on its own, it's not really a big deal. But if the conditions are just right, that little rhythm can turn into a wrecking ball. It sets the stage for something far, far more dangerous. You see, pretty much every object has what's called a natural frequency. Just think of a guitar string. When you pluck it, it plays a specific note. That's its natural frequency. Well, a crankshaft is no different. It has a speed that it wants to vibrate at. And at the same time, you've got the engine's firing pulses creating their own rhythm, which of course changes with engine speed. So what do you think happens when those two rhythms line up perfectly? That's when you get something called resonance. It's the exact same principle that lets an opera singer shatter a wine glass with just their voice. When the frequency of their voice, the sound waves, matches the natural frequency of the glass, the vibrations just build on each other and grow. And during resonance, the size of that twisting motion, the amplitude, it doesn't just add up. Oh no, it multiplies. It grows exponentially. The vibrations get dramatically, uncontrollably bigger, until they reach levels that are, well, potentially catastrophic. And that right there is the real danger. These massively amplified vibrations create an incredible amount of stress, and that leads to metal fatigue. We're talking about something that can literally snap a crankshaft clean in two. But it doesn't stop there. It can also shatter timing gears, shake flywheel bolts loose, destroy oil pump drives. I mean, it can create a whole host of really nasty noise and vibration problems. So when is the engine most at risk? You'd probably guess it's when it's screaming at red line at maximum RPM, right? Makes sense. But some fascinating research actually points to a surprising and much different truth about when the danger is at its peak. Yeah, check this out. A really detailed study on diesel engines found that the highest stresses don't happen when the engine is running along at a steady speed. Nope, they happen during what are called transients. Those unstable moments like starting up or shutting down. That's when the engine speed has to pass through those dangerous resonant frequencies. Just look at these numbers. Under normal, steady operation, the stress is maybe around 4,000 psi. But during coast down, when the engine's just spooling down on its own, it jumps to 12,000 psi. That's 3 times higher. And during a fast start, whoa, it can spike to over 23,000 psi. That's right, you heard me, more than 5 times the normal stress level. And this is all happening in just the few seconds it takes for the engine to fire up and settle down to an idle. It is an absolutely incredibly violent moment for the very core of the engine. So if starting up is that violent, it begs the question, how on earth do engines survive for hundreds of thousands of miles? Well, it turns out they have a silent guardian bolted right to the very front. It's called a harmonic balancer, or, to be a little more accurate, a torsional damper. Now, to you and me, it might just look like another pulley on the front of the engine, but it is a truly brilliant piece of tuned engineering designed for one specific job, to fight that torsional vibration. Okay, so here's the magic of how it works. The damper has 2 main parts, an inner hub that's bolted directly to the crankshaft, and then a heavy outer ring. And separating them is a layer of either special rubber or a really thick viscous fluid. So when the crankshaft starts its twisting vibration, the inner hub has to twist with it. But that heavy outer ring, its inertia makes it want to stay put, so it lags behind. And that tiny difference in movement forces the rubber or fluid to flex and shear, and in doing so, it absorbs all that twisting energy and turns it into harmless heat. Think about it. Without that damper, every single time the engine's speed passed through one of those resonant points, those chaotic, twisting vibrations would just build and build and build until something inevitably had to break. But with the damper, all of that destructive energy gets soaked up and turned into heat. That invisible threat we've been talking about, it's neutralized. And that's what allows the crankshaft to spin smoothly and reliably for thousands and thousands of hours. It's just an amazing reminder, isn't it, that inside the most common machines we use every day, there's this incredible engineering constantly at work, silently taming these invisible but hugely powerful forces, all to make our world run. It really makes you wonder, what other invisible forces are being managed all around us right now?